Why does gravity slow time? In everyday life, we usually imagine time flowing at the same rate everywhere. 1 second here should be the same as 1 second anywhere else. But Einstein's general relativity tells us something surprising. Gravity does not only affect motion. It also affects time. The stronger the gravity, the slower time passes. In this video, we will explain gravitational time dilation, why it happens, and why it matters for Earth, GPS satellites, and black holes. Here is what this video will explain. First, we will see what gravitational time dilation means. Then, we will ask why gravity affects time. Next, we will use spacetime to understand the idea more clearly. We will compare clocks near Earth and farther from Earth. We will also look at extreme cases near black holes. Finally, we will see real-world evidence from atomic clocks and GPS systems. The main idea is simple: gravity changes the rate at which time passes. In daily life, we assume time flows at the same rate everywhere. 1 second here feels the same as 1 second there. A clock on a table, a clock in another room, and a clock in another city all seem to keep the same time. For ordinary life, this is a very good approximation. The gravity differences around us are usually too small for us to notice directly. So our everyday experience tells us that time is universal. But general relativity shows that this is not completely true. Einstein changed the way we understand gravity. In Newton's picture, gravity is a force pulling objects together. That picture works very well in many situations. But general relativity gives a deeper explanation. Gravity is not just a force. Mass bends spacetime. And time is part of spacetime. So when mass curves spacetime, it affects both space and time. That is why gravity can change the rate of time. Gravitational time dilation means that time runs at different rates in different gravitational fields. A clock closer to a massive object runs slightly slower. A clock farther away, where gravity is weaker, runs slightly faster. Near Earth, this difference is extremely small. But it is real. It can be measured with very precise atomic clocks. The closer a clock is to a strong gravitational source, the more slowly it ticks compared with a clock far away. Stronger gravity means slower time. Black holes show gravitational time dilation in an extreme way. Near a black hole, gravity is incredibly strong. A clock near the event horizon would appear to run much slower when seen by a distant observer. As the clock gets closer to the event horizon, the slowing becomes more extreme. To a faraway observer, time near the event horizon can seem to almost stop. This does not mean time feels frozen for someone falling with the clock. It means different observers compare time differently in strongly curved spacetime. Near a black hole, gravity can make time appear to stand still from far away. The stronger the gravity, the stronger the time dilation. In weak gravity, the effect is small. A clock far from a massive object runs faster than a clock close to it. In strong gravity, the effect becomes much larger. A clock near a very massive object runs noticeably slower compared with a distant clock. This does not mean the clock is broken. It means time itself is passing differently in that gravitational field. The closer you are to a massive object, the slower time passes. Black holes show gravitational time dilation in an extreme way. Near a black hole, gravity is incredibly strong. A clock near the event horizon would appear to run much slower when seen by a distant observer. As the clock gets closer to the event horizon, the slowing becomes more extreme. To a faraway observer, time near the event horizon can seem to almost stop. This does not mean time feels frozen for someone falling with the clock. It means different observers compare time differently in strongly curved spacetime. Near a black hole, gravity can make time appear to stand still from far away. Gravitational time dilation is not only a theory on paper. It has been measured using atomic clocks. Atomic clocks are precise enough to detect tiny differences in the rate of time. This effect also matters for GPS satellites. GPS satellites carry very accurate clocks while orbiting high above Earth. Because they are farther from Earth's gravity, their clocks run slightly differently from clocks on the ground. GPS systems must correct for relativity. Without these corrections, navigation errors would quickly grow. Modern GPS works because gravitational time dilation is real and measurable. A common misconception is that time dilation is just a feeling. Someone may think time feels slow because they are bored, tired, or waiting for something. That is psychology. Gravitational time dilation is different. It is a real physical effect. Clocks actually tick at different rates in different gravitational fields. A clock in stronger gravity runs slower. A clock in weaker gravity runs faster. This can be measured, tested, and used in technology. Time dilation is not just an illusion. It is a real feature of spacetime. Let us now gather the key idea. Gravity affects time because time is part of spacetime. Mass curves spacetime. And that curvature changes how time passes. A clock in stronger gravity runs slower. A clock in weaker gravity runs faster. The effect is tiny near Earth, but extreme near black holes. It is also important in real technology, including GPS. The key takeaway is simple: gravity changes time. Thank you for learning with Prep for Uni Online. If you want to understand relativity more deeply, continue with our lessons on spacetime, general relativity, black holes, the speed of light, time dilation, and modern physics. Prep for Uni Online provides free university preparation resources for students exploring physics, engineering, science, technology, mathematics, humanities, business, health, and the arts.